right, in chapter 2, we're going to look at the chemical level of organization. So chemistry, guys, is the science that studies composition and properties of substances, or what we call matter. Now, we're not going to spend a lot of time on certain parts of chemistry, but we are going to be looking at especially at those biomolecules that are super important for us to survive. So cells are living, and they are composed of chemicals which are non-living. So this is again why we would look at chemistry. Our body relies on chemical reactions, which we call metabolism, in order to maintain homeostasis. So let's take a look at atoms of elements. So all living and non-living things are composed of matter. So matter is anything that takes up space and has mass. Now it can take 3 forms. It can be a solid, liquid, or gas. Now this should be reviewed. An element is the building block of all matter. There are 92 naturally occurring elements with 118 different elements. Each has a unique chemical symbol. We represent this with a letter abbreviation. 26 of them are found in our body. Now this is important because these 26 are required in order for us to survive. Now the major elements are shown here in this pie chart, and they're a huge percentage of the elements needed for us. However, there are some lesser elements and some trace elements which are also important. Over here you can also 65% of your body is with oxygen, 18 is carbon, 10 is hydrogen, 3 is nitrogen, and then the rest of the other types of elements. So the major elements are going to consist of carbon, hydrogen, oxygen, and nitrogen. Your lesser elements are going to be things like calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, and iron. So these are going to make up your major elements as well as your lesser elements. If you take a look here at this table, you're going to see that we're going to focus in mostly on oxygen, carbon, hydrogen, and nitrogen. However, you can also see the lesser elements are listed here and what they are important for. So guys, an atom is the smallest unit of matter. It's what the different elements are made of. All atoms of the same element have a similar atomic structure. So in order for them to be part of the same element, the atom needs to be similar. Now, atoms have certain parts to them. Okay, they have a nucleus. Don't confuse this with the nucleus of a cell, but this nucleus is where protons and neutrons are found. The electron shell is where electrons are found. These are also known as energy levels. So when we take a look at this, guys, protons are the positive charged particles of an atom. Neutrons are neutral. They are both going to be found in the nucleus. Electrons have a negative charge, and they are going to be found in the electron shell. These electrons are contained in orbits. So you kind of think about it as like the nucleus is kind of like the planet, and your electrons go around kind of like the moon goes around Earth. Now, they have to fill the innermost shell first before moving to the outer shells, and the first shell is full when it has 2 electrons. Once the inner shell has 2 electrons, we can go to the next shell. The second shell is full with 8. The third is full with 8 as well, and so on. We call this the octet rule because as long as it has 8, then they are generally happy. They will not react anymore. So let's do a quick overview of these particles. So a proton has a positive charge, a neutron has no charge, it's neutral, and an electron has a negative charge. Now, AMU is the atomic mass unit, how much it kind of weighs in a sense. Now, this is super small, so they had to make up its own category, and that's why they call it an AMU. Protons have a 1 weight of AMU. Neutrons also have a 1, and guys, electrons are so small, they are going to be given a 0. This does not mean that they weigh nothing, but they weigh so little that we don't need to really take it into account. Location-wise, remember that the protons and neutrons are both found in the nucleus, whereas the electrons are found in those orbits or shells around the nucleus. So here in the diagram, you can see that you have the nucleus with protons and neutrons. The first energy level is going to be full with 2 electrons. The second and third will be full with 8. Now these shells go from having less energy closer to the nucleus to having more energy as they move away from the nucleus. So guys, here's the periodic table of elements. This is standardized across the world. You would find that the periodic table is going to be something that does not change from country to country. However, the characters and the way that the numbers are represented might be a little different based on how that country does it. But the first element is always hydrogen, no matter what periodic table you're looking at. When we look over here, 6, every time you look at a periodic table, number 6 is going to be carbon. Number 9 is going to be fluorine. Number 30 is going to be zinc. That's the same in every periodic table. So let's break this down and let's just look at how to read one of the boxes in the periodic table. So when you look at the periodic table, it's going to have a letter. This letter is the atomic symbol of the element. It also is going to have 2 different numbers. The smaller number is the atomic number. This is the number of protons, and this is going to be the number that is always a whole number. There's no decimals with this number. So this is the number of protons. So this tells you that all carbon atoms have 6 protons. Right? That's what makes it a carbon atom. On the other hand, the other number is the atomic mass. How much does it weigh? And this is going to be your protons plus your neutrons. This number could be a decimal found on the periodic table because not all carbon atoms have to have the same number of neutrons. They do have to have the same number of protons, however. So how do we determine the number of subatomic particles of an atom? So when we look at this, guys, the number of protons is the atomic number. So in the case here for carbon, that would be 6. The number of neutrons is the atomic mass minus the atomic number. Again, in this example, that would be 12 minus 6, which is 6. And the number of electrons, when we're talking about a neutral atom, is going to equal the number of protons. This means our negatives have to equal our positives. Well, we already know there's 6 positives, so this means there would be 6 negatives, which are the electrons. Because, guys, atoms are neutral in charge. So let's take a look at carbon again. The number of protons would be 6. The number of electrons is going to equal the number of protons, which is 6. And the number of neutrons is going to be 12 minus 6, which is 6. Okay, so 12 minus 6. This would be kind of the pictorial representation of what a carbon atom looks like. 6 protons and 6 neutrons in the nucleus. And then we see that you have in the first energy level 2 electrons, and in the second energy 4, because 4 plus 2 equals 6. This one has 6 electrons. So let's take a look at the atomic structure of some of these other elements. So if we take a look at hydrogen, how many protons does hydrogen have? It has 1. How many electrons does hydrogen have? Well, we have to have the same number of positives and the same number of negatives, so it's 1. And then the number of neutrons here is 0, because 1 minus 1 is 0. In this case, this hydrogen has no neutrons. Okay, what about over here for nitrogen? If we look at nitrogen over here, we can say the number of protons is 7. Remember, it's the smaller whole number. There's 7 positives, therefore there should be how many negatives? There should also be 7. To find the neutrons, we would take 14 minus 7, which is 7. Are we seeing a kind of routine here? It's not always going to be this way where they're all the same. For oxygen, oxygen has 8 protons. Since it has 8 positives, it needs to have 8 electrons for negative. And 16 minus 8 is going to tell us there are 8 neutrons. So this is how it would work with reading and determining what we have in these atomic structures. So just a reminder, the number of protons, electrons, and neutrons are not always going to be the same. I know in some of these examples they were, but they're not always. So guys, atoms are neutrally charged, meaning the number of electrons equal the number of protons. However, ions, on the other hand, are charged particles. This means that the electrons and protons do not equal each other. We maybe will have more negatives, or we may have more positives. So in this example here, this is showing you the sodium atom. Remember, atoms are going to be neutral, which means there's 11 protons, and if you count the dots, there are 11 electrons. However, if a sodium atom loses an electron, this electron in this outer shell, they give it away or it gets lost. That means it has lost a negative. This means there are now 11 positives and there's only 10 negatives. Since they do not equal each other, this creates a sodium ion. Right? So this would be a positive ion because it has extra protons. If it had extra electrons, it would be a negative ion. Another thing that can be different are what we call isotopes. Isotopes are atoms with a different number of neutrons. So they are still carbon in this case, carbon 12 and carbon 14. And in order to be carbon, this means they have 6 protons. However, when we do 12 minus 6, this shows that this particular carbon atom has 6 neutrons. But if we do 14 minus 6, this one shows that this one has 8 neutrons. They're still carbon, but the neutrons, since they have a neutral charge, just make the carbon 12 lighter than the carbon 14, because the carbon 14 will be heavier since it has more neutrons. Now, these isotopes can be very unstable. However, we can use them in a number of ways, and we use them a lot of times as tracers when we do certain kinds of x-rays, CT scans, MRIs, that kind of thing. But we also use a lot of these isotopes to treat cancer. So some concepts to review for this little bit of chemistry. The outer shell of the atom likes to be full. It wants to get a full number, and in the case of the first shell, it's 2 electrons. The second and third shells want to get 8 electrons. Ways they can fill their outer shell is they can give up or donate electrons to another atom. This is going to cause it to become an ion. If it gives negatives away, it will be a positive ion. Others can accept electrons. That means they take extra electrons from those atoms. This means they have extra negatives, so these would be negative ions, or they could share with one another. All of these, no matter if they're giving, taking, or sharing, they are going to result in some sort of chemical bond, which is what we're going to talk about next. Electrons in the outer shell are the ones that participate in these chemical reactions or chemical bonds. Atoms of inert elements, they have a full shell of electrons, so therefore they're non-reactive. These are examples like neon. These are known as the noble gases because they do not react with anything because they're full and happy. They don't need anything from anyone. So these are found on the periodic table over here on the far right-hand side. The noble gases are inert, they're full, their electron shells are full, so they will not react with other elements. So this brings us to the idea of what molecules and compounds are. Now we're going to actually see these atoms interacting, and so this is going to create things like molecules and compounds. So a molecule, guys, is a result when 2 or more atoms chemically combine. All right, so 2 or more atoms chemically combine. A compound is where a molecule contains 2 or more different elements. So guys, in a molecule, they can be the same elements, but in a compound, they cannot. We also see free radicals can happen. This is where they have unpaired electrons in their outer shell, and this is what causes them to be reactive and damaging to our body, but gives them a charge, like a negative or a positive. An example of this are superoxides, and they can be inactivated by antioxidants. So if we take a look here, here's a little quiz. Is it an element, a molecule, a compound, or a superoxide? So this first one is just oxygen. It's oxygen by itself, which means it is an element. The next one is H2O, which is water. It has 2 hydrogens and 1 oxygen. Is this an element, molecule, or compound, or a superoxide? In this case, we see that it is a compound. However, it could also be termed a molecule. It's 2 or more atoms that combine. But a compound has to have 2 or more different elements, which you do see here. There are hydrogen and there are oxygen. On the other hand, for O2, is it an element, molecule, or compound, or a superoxide? In this case, O2 is a molecule. They are the same, so it cannot be a compound. Now, if O2 has extra electrons that are unpaired, it becomes negative, and this is what we see with a superoxide. Note, not all molecules are compounds, but all compounds are molecules. Sometimes the term compound and molecule can be used interchangeably, but you need to be careful with this. Remember that a molecule is 2 or more atoms, but a compound means they have to be different. All right, so keep that in mind. All right, so now we're going to be looking at our chemical bonds. Okay, we talked about how these electrons are going to be either given away, taken, or shared, and so let's look at how this bonding takes place. The first type of chemical bond is known as an ionic bond. This is formed when atoms of elements give up or accept electrons. This is the type of bonding associated with inorganic molecules like table salt, NaCl. So a cation, see ions on there, which means it's charged, is a positively charged ion. In this case, it's the sodium because it gave away an electron. An anion is a negatively charged ion, which means that it gained an electron. It has now more negatives than positives. This would be the chlorine. So now sodium has a positive charge, chlorine has a negative charge, which means they are opposites. Since they are opposites, they now attract. Okay, just like a north pole and a south pole of a magnet are going to attract, the same thing happens here. Opposites attract. So ionic bonds are formed due to the interaction between ions, a positive ion being attracted to a negative ion. Now, electrolytes are something that are important for us to survive, and they form when ionic compounds break apart into some cations, some positive ions, and some anions in solution. These are going to be like sodium, chlorine, bicarbonate, and potassium. They are going to be helpful in helping our cells function properly, but they're created when ionic bonds are broken. The next type of chemical bond is called a covalent bond. This is formed when atoms of elements share their electrons. This is a type of bonding associated with organic molecules. Now, covalent bonds could be a single bond where they're just sharing one pair means two, so they're sharing a pair of electrons. A double means they're going to share two pairs of electrons, which means there's 4 electrons. And a triple means it's going to share 3 pairs of electrons, which means they're sharing 6 electrons. Okay, because remember, a pair means there's got to be 2. All right, now this sharing that's taking place could be equal. If it's an equal sharing, this is known as a non-polar covalent bond. This means they all share the electrons equally. Kind of think about it like in the year where the electrons would spend 6 months with this atom and 6 months with the other atom. All right, so they're sharing equally. It's an equal amount of time. We see this right here with methane, which is CH4. Those electrons are spending the equal time with carbon as they are hydrogen. If the sharing is unequal, this is known as a polar covalent bond. This is going to be what we see with water, H2O. Oxygen is larger than the hydrogens, and so because of this, it pulls the electrons more often. So in my example of the year, instead of spending 6 months with oxygen and 6 months with hydrogen, it's now spending 9 months with oxygen and only 3 months with hydrogen. It's unequal. So because of this, we see that oxygen, because it has the electrons more often, gets a little bit of a negative charge, whereas the hydrogens are going to have the electrons less often, so they have a little bit of a positive charge. This is what creates those poles, because a pole, north and south pole, they're opposite. So I have a negative side and I have a positive side. Now again, covalent bonds can be single, double, or triple. These are going to be polar or non-polar. So when we look at these single, double, and triple bonds, if they are with the atom that is the same as them, like hydrogen to hydrogen, oxygen to oxygen, nitrogen to nitrogen, they are going to share equally. So these, if they're sharing equally, are considered non-polar. Another type of interaction that can take place are called hydrogen bonds. Now, hydrogen bonds are a weak attraction between molecules. This is not actually between atoms of the same group. It's going to be one molecule being a little bit attracted to another molecule. This is really big between water molecules and within DNA. So what happens here with these water molecules, remember that they're polar. Since they're polar, they have a negative end and a positive end. So this water molecule is attracted to the next water molecule, which is then attracted to another water molecule, and it causes the water molecules to start to stick together. This is why when a drop, like when a raindrop lands on your windshield, it kind of sticks all together as one big drop in that sense. Okay, and it's gonna stick together on your car. Or have you ever filled a cup up where it's right at the brim and it just kind of, you thought it was going to spill over, but it just makes like kind of this dome? It does this because of the hydrogen bonds. Hydrogen bonds are also a big deal in DNA. If you remember with DNA, it's a double helix, 2 strands held together by rungs in between. Those rungs are held together by hydrogen bonds. Now, chemical reactions involve making and breaking chemical bonds between these atoms, and so the reaction is whether we make the bond or break the bond. Now, the reactants are what goes into the reaction. The products are what comes out. So the arrow always points towards the products. So reactants are inputs and the products are the outputs. There are molecules in our body that can actually help speed up this reaction from reactants to products, and they are known as enzymes. Most of the times enzymes end in ase. So this would be something like sucrase, amylase. Those are enzymes who help speed up reactions. So in this particular case, I have two H2 molecules plus an O2 molecule. These are going to interact. These are the reactants which are going to go in, and when they interact, we're going to form two water molecules. So the bonds between the hydrogens broke apart, the bonds between the oxygens broke apart, and they formed new bonds to create a new product. In order to break these bonds and cause this reaction to begin, this is called energy of activation. It's the energy required to initiate the chemical reaction. Enzymes are a catalyst, which is going to lower the amount of energy needed. All right, it's going to make it easier because we don't need as much energy added. Chemical reactions continually occur within cells, which is referred to as our metabolism. Remember, our metabolism is the sum of all of our chemical reactions in our body. So if we take a look here, this is showing you the reactants coming in order to get them to actually change and become products, we have to put some energy into this. So we have to go up with the energy, and then the products can be made. Hey, this is the activation energy. When we add enzymes to this, however, it can actually bring that energy down. So the red line is showing you what happens in the normal reaction, and the blue line is showing you what happens when you add an enzyme. See how it can happen faster? It does not take as much energy to start the reaction. So the red is no enzyme, the blue is with the enzyme. So some examples of two major types of chemical reactions that we want to talk about are synthesis reactions and decomposition reactions. Now, synthesis reactions are where I'm going to take two separate things, A plus B, and I'm going to push them together. I'm going to make something. This is where synthesis comes in. Decomposition is the opposite. I started with something larger, A and B, and I'm going to break it apart into A plus B. Decomposing it, deconstructing it, breaking it apart. So synthesis reactions are like when I take a glucose plus a glucose and I'm going to push them together to make maltose. All right, I'm making a larger molecule. A decomposition reaction would be the opposite. I take the larger molecule, maltose, and I break it apart into glucose plus glucose. All right, so these are opposites. Synthesis reactions are also known as anabolic reactions because they build things, and decomposition reactions are known as catabolic reactions because they break them down. Now, synthesis reactions, because we're building something, requires energy to go into it. Okay, think about it. If you're going to build something like a house, you've got to put resources and energy into that process. Okay, so this is an endergonic reaction. On the other hand, if you were going to tear it down, okay, it's an exergonic. Energy is released from it. That's why you have to wear a hard hat and be careful with that, because as it falls down, energy is being released. So that's an exergonic reaction. So when we build things, we put energy in, and when we break them apart, we release the energy. All right, so here's an example. Is this a synthesis or decomposition reaction? Okay, we have here C6H12O6, which is a glucose molecule plus oxygen. It's going to get converted into water, H2O, plus carbon dioxide, and energy. All right, so is it synthesis or decomposition? The hint here is that energy is being released. It's going out. So this is an example of decomposition. It's a decomposition reaction. So here are some concepts. When chemical bonds are broken, energy is going to be released. Okay, energy is going to be given off. When chemical bonds are formed, energy is going to be required, and it's going to store that energy in the bonds. Energy released during decomposition reactions can be used to drive synthesis reactions. Okay, so the energy that comes out of breaking it apart can be used to build something new. All right, so the energy that comes out of one reaction can go into another reaction. Metabolic reactions involve energy conversions. This is so the cell can do work. So energy is the capacity to do work, and it takes lots of different forms. Potential energy is stored energy. This is energy that's stored in those chemical bonds, in that food. If we want to access that energy, you have to eat it. You have to break it apart. You can't just look at that meal and be like, man, I just got a ton of energy from it. You have to actually consume it and break it apart. Kinetic energy is the energy of motion. This is going to be what we're going to do with that potential energy in order to create movement and transport within your body. There is a law of conservation we want to look at. This is the first law of thermodynamics. This says that no energy can be created nor destroyed. Okay, so we can't make new energy. We have to get it from it being stored, and we can't destroy the energy. However, the second law of thermodynamics is called the generation of heat. This means when we actually break bonds or form bonds, some of the energy is going to be transferred as heat. Think about it. You put gas in your car. The gas is potential energy. When we start your car, the gas moves through the engine, which allows the car to move. However, when you get out of the car after you've driven for a while and you fill the hood, what do you feel? You feel heat coming off of it, because that conversion from potential to kinetic energy caused some of that energy to be released as heat, which is a type of energy. All right, so this is going to be part 1 of your chapter 2, where it gives kind of a overview of chemistry. In part 2 of chapter 2, we're going to get into inorganic versus organic molecules, and we're going to get into those organic molecules that are required for life, like things like carbohydrates, proteins, nucleic acids, and fats.